Look at these strange shapes. These are 3D representations of complex D and F atomic subshells. Once you move past simple atoms, calculating where every electron lives in these bizarre, vibrating orbitals gets incredibly complicated. But you don't need to memorize a massive list of configurations. You can write the exact structure for any element by simply reading the periodic table left to right, just like a book. To see how this works, grab a blank periodic table and a few highlighters so you can follow along. By applying 3 simple mathematical rules, we are going to turn this standard chart into a universal cheat sheet that tells you exactly where every electron goes. First, number rows 1 through 7 down the left to represent energy shells. Next, box the 4 main sections: S block, P block, D block, and F block. Finally, move helium from the far right to sit directly above beryllium in the S block. Rule 1. In the S block and P block, the energy shell matches the row number. Tracing across row 2 shows this. Passing the magenta block adds 2 electrons to the 2s shell. Crossing the orange block adds 6 electrons to the 2p shell. For these standard blocks, you don't have to guess the quantum energy level. You just look at the number on the far left. In the middle D block, let's use iron as our test case. Reading the table top down to iron builds our baseline string. We get 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. But then we hit the green section. This is where our second rule comes in. Whenever you enter the D block, you must subtract exactly 1 from the row number. Iron is in row 4. Applying the rule, 4 minus 1 tells us the D block elements here belong to the third energy shell. Now we just count the spaces across that green block until we land on iron. It's the 6th space. We take that shell number, 3, and our count, 6, and cap off our sequence with 3d6. This shift happens because the third energy shell actually has plenty of room to hold these extra 10 electrons, but they only begin to fill once the fourth energy shell has already started its own layer. Down at the bottom, we have the detached rows. These are the lanthanides and actinides, and they actually squeeze right into the gaps in rows 6 and 7. Our third rule handles this heavy F block. You always subtract 2 from the period number. If you read across row 6 and hit that blue F block, you subtract 2, dropping you immediately into the 4F subshell. With those rules in place, let's look back at iron's final sequence, ending with 4s2 and 3d6, and ask which of these electrons actually interact with other atoms. This basic atom model shows valent electrons sitting in the absolute outermost ring, furthest from the nucleus, regardless of energy state. Even though electrons in ring 3 are in a higher energy state, ring 4 is physically wire. Because that 4s shell forms the physical exterior of the atom, iron possesses exactly 2 valence electrons. Identifying these outer electrons is an architectural problem. Knowing their physical distance from the nucleus is how we determine how an element will chemically bond with its environment. Look down at the physical map you've just created. You have the primary blocks mapped out. The S and P blocks equal the row number. The D block equals the row -1, and the F block equals the row -2. You are no longer navigating a static list of symbols. You are using a coordinate system that accurately predicts the internal structure of every transition metal. Try it yourself. Pick a random massive element from the bottom rows and write out its complete configuration using only your subtraction rules. The periodic table is a functional blueprint. Once you know how to read the grid, the configuration of every atom is right there in front of you.